In this video, I'm going to go into the first steps of solving differential equations. And I'm going to work through some examples. I want to let you know from the beginning, we're not going to go into obscure details like existence of solutions and continuity of solutions and so on, because those are of no interest to students of engineering or even of science, or certainly not those doing higher school mathematics for their entrance exams. So what I'm going to concentrate on is giving you certain types of differential equations and going through the methods of solving them. So starting off with just about the most elementary type, and I've given it here as number 1, saying that dy dx is equal to x squared. To solve this, all we have to do is integrate both sides with respect to x. And I've written down the integral sign here. Integral of dy dx with respect to x equals the integral of x squared dx. On the left-hand side, you can consider the dx's as cancelling out. And so we end up with this next step here, which is the integral of dy equals the integral of x squared dx. Integrating both sides, the left-hand side becomes y, the right-hand side becomes x cubed over 3. And I've added on a constant c. Now, in this particular form, this is what's called the general solution to the given equation. If we want a particular solution, we need to know what are known as initial conditions. In other words, what x equals at a given value of y. Okay? Right. So this is an example of a variable separable type of differential equations, which are just about the most simple of all, although the integration step may not always be too simple. For the second example, I've got dy dx equal 2 sine x plus 3 cos x, where we go through the same procedure as before, integrate both sides, or first of all, write the left-hand side as the integral of dy equals the integral of 2 sine x plus 3 cos x dx, and then perform the integration. The left-hand side becomes y, and the right-hand side becomes minus 2 cos x plus 3 sine x plus c. So that deals with that. Again, c can only be found if initial conditions are given. For the third question, we've got dy dx equals 2x over 1 plus x squared. I'm going through the same procedure. We got the integral of dy equals the integral of 2x over 1 plus x squared dx. Integrating, we get y equals log of 1 plus x squared, because the right-hand integral, the numerator, is the exact differential of the bottom, and so the integral is the logarithm of the denominator. So that's y equals log to base c 1 plus x squared, and then add on the arbitrary constant. For the next one, I've given what's called a second-order equation, because it's got the second derivative of y with respect to x equals 2x squared minus 5x plus 7. Integrating step by step, the left-hand side becomes dy dx, and the right-hand side becomes 2x cubed over 3 minus 5x squared upon 2 plus 7x plus an arbitrary constant a. And then in the next step, again integrated step by step, and we get dy dx becomes y, and the right-hand side becomes x to the 4th over 6 minus 5x cubed over 6 plus 7x squared over 2 plus ax plus b. So we notice here that we have have two arbitrary constants because this is what's called a second-order equation. We've had to integrate twice, and that's why we've got two arbitrary constants. And so in this last question, number 4, we have to be given two initial conditions in order to find the values of A and B. We'll do much more of that later on. So, in the 5th and last example for this opening session, we want you to find the unique solution of the equation x plus 3 dy dx equals 5x squared y squared, given that y is equal to 1 when x is equal to 0. Separating the variables, on the left-hand side we will get dy over y squared equals, on the right-hand side, 5x squared over x plus 3 dx, which can be rewritten as 5x minus 15 plus 45 over x plus 3 dx. Performing the integration, the left-hand side becomes minus 1 upon y, and the right-hand side becomes 5x squared over 2 minus 15x plus 45 log x plus 3 plus the arbitrary constant c. Now, since y equals 0 when x equals 0, plugging those into that equation, we'll get minus 1 equals 45 log to base e3 plus c, so that c is equal to minus 1 minus 45 log to base e3. And so we end up with minus 1 upon y equals 5x squared over 2 minus 15x plus 45 log to base e x over 3 and minus 1. Or we can write that in a slightly different form, inverting both sides. Then y will equal 1 over 1 minus 5x squared upon 2 plus 15x minus 45 log to base e x plus 3 over 3. Well, that brings us to the end of this opening session, and thank you for listening.